So if you recall last time, what we did is we saw some submodular functions and we looked at submodular maximization. Okay. Okay. So the best way to submodular function. Okay. And what were our submodular functions? So we suppose we have n is a universe, and then there's a function from 2 to the power n to some r. Okay, and the best way to view some modular function is imagine yourself that you are an industrialist I1 and you are an industrialist I2. Okay, and you have opened company for some set of facilities, like both of you, right? Now, I want to make some new item. I want to make some new item, right? For example, imagine Apple has it has been making MacBook and whatnot, and suddenly he decides to make iPad or iPhone, right? It has already some existing things which he can use to make this new product, right? But someone who has to suppose, imagine that start from scratch, he needs the cost to build a new product is going to take much more cost than this. And this is why when we say look at S and look at T, where S is a subset of T, right? And I want to make one new item, cost to make one new item, like adding one new item to S, like is much more than maybe I already had much more things, then I am making a new thing. So this is why cost of S union E in terms of cost function, so you can write f of S union E minus f of S, like given S I'm making S union E, is more than f of T union E minus f of T. Because more things I have already made, the cost to make a new item will be much cheaper compared to cost of making a new item when I have a small number of facilities open for that, right?
This relation is for S and T without any relation?
No, S is subset of T. Yeah, for all. And this is equivalent to the normal definition of this. Okay? But this is the one which we must learn. Like this tells us marginal utility of any item to be added. Right? So like if I add one item, like what is the marginal contribution do you get? And the right way to think about, and this is why these functions comes in lots of game theory and this and that, because of this way of looking at, like someone who's doing some welfare maximization and this and that, then this is where the cost function will come. Okay, so these are interrelated objects. So this is the right way of looking at some modular function. But the definition which we all the time we see, so last time I used this, but I didn't tell you like why was this coming. So this is the basic principle which governs some modular functions. Okay, so what did we? So we proved last time that first of all, for all S subset of T, E in n minus T, f of S union E minus f of S is at least f of T union E minus f of T. So given T, making a new item is much cheaper compared to when I have a small subset of items that I have made. Right? And this is how market, so if you look at a company which is making a suddenly new product, right? It doesn't make completely orthogonal new product. It makes a new product which is based on the current set of products, so that it is easier to utilize the current facilities to do that. Boeing is not going to make suddenly something, right? Boeing makes 737 and then tries to make 757 or whatever it is. Why? Because they already have the basic principles of making aviation or this and that. Only thing they need to have new set of conditions imposed, like, oh, it should be cheaper, like it should be lighter, or it should go much farther. But the basic structures remain the same. All they need, oh, what kind of material do I need? But they have an assembly line ready for that anyway, right? So that is why most companies or industries, they try to make things which is very closer to what they were already making. And this is also true about social welfare schemes and this and that, right? So this is the right way of looking at it. But in general, so the equivalent definition is, which we proved last time, is that for any s comma t, now there is no relation between them, f of s plus f of t is greater than or equal to f of s union t plus f of s intersection t. Okay? Okay. So what was our greedy algorithm doing? So now this is it. So there are two questions. Okay. What I can ask is the following thing, right? So I can ask minimize x subset of n f of x. Return me this, right? This is a minimization function. This is polytime under certain number of query hierarchical model. But if I do maximization x subset of n f of x, then this is NP hard. Why? Because let's encode max cut, right? What do I want? I want to output x which minimizes and maximizes the number of edges going out of it, right? So so this is an unconstrained version. I'm not putting any constraint on the size of this, right? So this is NP hard. Okay. Now, or maximum k coverage or some such things it can model. Okay. So there are two versions, unconstrained version, or so let's call it unconstrained submodular maximization and submodular maximization. Okay. When I say unconstrained submodular maximization, I will mean that apart from like I don't care about the size of x. Okay, submodular maximization, constraint submodular, and here constraint can be many things. But we have been only talking about cardinality constraint. So what I want, not only anything mod less than equal to k. Okay, there are different versions of the questions. Some question asks you to produce exactly mod s equal to k. Someone asks mod less than equal to k. There are why I call constraint submodel. I also give you on n a matroid, and I ask you no. I do not want any s, but I want s which is independent set of the matroid. Okay, so this is called submodular maximization, constraint submodular maximization under this. Then there is also a knapsack constraints. That like people have studied all kind of things based on their need and requirement. Okay, what we will do. I do not remember very well, but you can also put some knapsack constraints. Right? Yeah. Okay. Right. So what was our greedy algorithm last time? So but now we divided our types of functions into two types. One is f is monotone. And what does f was monotone mean? For all x subset of y, f of x is less than or equal to f of y. Right? This is what the monotonicity means. Okay? But it is not true about any arbitrary functions. If I take arbitrary submodular function, xn, even if x is subset of y, it doesn't mean that f of x has to be less than or equal to f of y. Okay? So what did we prove last time? This is a theorem we proved last time. That if f is non-negative and non-negative, monotone and submodular, then for cardinality subset maximization, we are looking for mod s less than or equal to k or equal to k, it doesn't matter, has 1 minus 1 by e approximation. Right? What does it mean? So if there is an opt, right, I will give you a set x such that the value of f of x is at least 1 minus 1 by E times f of opt. This is what it means. Right? And what is the property? All opt of size at most k, all x of size at most k. But here opt equal to k and mod x equal to k doesn't matter, because I find any solution, then I arbitrarily add a couple of elements so that it becomes k because of this property. Value will not change. But I cannot do this when I assume that the function is arbitrary. Okay? So the algorithm was very simple. The algorithm was pretty simple, and what was the algorithm doing? If you recall correctly, so random greedy. Okay? So it takes a function f and k, and if you recall, let a0 equal to empty set. And what did we say? For I equal to 1 to k, do. Right? Let ui be element in n. Okay? Let ui be element in n, maximizing f ui given ai minus 1, which is same as what happens if you add ui to this, right? So among I1 to k, I just go ui, and whatever current set I have, I just pick the one which maximizes my utility, which maximizes my utility, and I just add that. This was the end of the algorithm, right? Oh no, this is not random. Sorry, this is greedy. There's no randomization. This was my mistake. Sorry. Let ai equal to ai plus ai minus 1 plus ui return ak. Right? This is what we did last time, and we showed this particular algorithm has this factor approximation algorithm. Okay. Now, what did we also showed, or we tried to show, is that what happens when we try to do, right? So this condition is same as saying, well, if f of ai minus 1 union ui is greater than or equal to f of ai minus 1, then just add it. Right? That's it. So same thing as that, but it could give you a small, like I only add an element if it is positively increases my value. Okay? And then even if it's less than k, as I told you, it's a monotone function, I can just add some other elements and make it equal to k if required. Okay. So let n equal to a1, a2, an, okay? This is my universe. And I define a non-negative submodular function f by f of s equal to 1 if mod f equal to 1 and f equal to a1. So this guy, if look at, because I have to give a function from 2 power n to r positive. Okay, I'm trying to give a function of this nature. Okay, so f of s is 1 if mod s equal to 1, s is equal to ai, a1. Half if mod s is equal to 1 and s is not equal to a1, right? 0 if mod s is greater than or equal to 1 and a1 is an element of s, 1 or okay, summation ai in s f of ai otherwise. Okay. So we claim that this is a submodular function. Right? So what did I do? First of all, I gave ai a1 value 1 and any subset which contains a1 value 0. Okay. So now if you look at here, right, any set which contains A1 is left hand side is going to be 0 if it contains S contains A1, like here is S, here is T. Okay, so it doesn't matter, right? Suppose S A1 is here, then A1 is already 0, right? F of S is what? This is also 0, right? Because I have added some element, already S contained this, so this is 0 until unless S itself is like A1, right? Suppose S is A1, then what happens? S union U is 0, right? Minus F of S is like minus 1. I have to show this is greater than equal to. So what is F of T union E? Is 0. And what is F of T? What is F of T? Huh? It could be minus. If A1 is in S. Maybe some other inequality is better.
But here, are you given F and you are also defining F?
No, I am defining an F to show that this greedy is very bad for like arbitrary function.
Oh, okay.
I'm trying to give. So I'm trying to.
An arbitrary function which is not monotone and it is bad.
Then this greedy algorithm is not going to give you anything. This is what I'm going to do. Okay. So first I have to show that this is non-negative by definition. That's okay. Why it is submodular? Maybe we can use one of these inequalities to show. What happens if S is A1? Okay. I added. Okay. So if S contains A1, T also contains A1 by definition, because E is element which is outside both. You have to look. So what is F of S union E? 0. What is F of S? Is 1, right? So minus 1. What is F of T union E? Is 0. And what is F of T? It is 0.
No, it will be 0, right? Because it's a superset.
Which contains A1.
Yeah, it means 0, right?
But left hand side we get minus 1.
So which is not. So then it is not submodular by definition, right?
It looks like, no? Did I do something wrong? Just for example, what happens if I take A1 is our S, A1, A2 is here, and E is here, right? Then S union, so this is 0 because it has two elements, contains A1, so this is 0 for sure. This is F of S, which is 1 because it is just S equal to A1, so I get minus 1, right? But T union E is 0 because it is two element set, and added E1, and I added F of T 0. So this is 0 and this is minus 1. This is like, no, this is something. Did I do something more? Maybe I didn't write the definition correctly. Wait. No, no, this is correct. This is correct. This is nothing. No, no, this is correct.
This definition, f of s definition.
F of?
Here, the right hand side. Something may be wrong here.
Doesn't look like.
Oh,
This is something. Maybe this is something.
with your non-negative.
Non-negative weight function.
We switch 0 and 1.
Hmm?
Should we switch 0 and 1?
No. This is something which I do not want to do. For other, this is fine. I mean, if it doesn't contain A1, then it is fine. Right? Because what? Yeah, but if A1 is not in S, A1 is not in S. Otherwise, what are we doing? Okay, let's try some other function. Maybe this is bit, but it should work. But fine. Let me try some other function. F of A. So I fix some element A1. Okay. Okay. So what do I do? F of A is cardinality of A1. If A1 is not in A. Okay. And two otherwise. Okay. Now what happens? So suppose S consists of A1. Yeah, then this is fine, right? Because yeah, if you contain A1, your value is always going to be 2. For all sets which contains A1, your value going to be 2. So if you contain A1, then 2, 2, 2, 2, and you are done. So this is fine. Okay. Okay. It's not in 1. Okay. So now what happens? Look at the approximation algorithm, right? Now it is easy to show this is fine, right? Either it contains A1, it doesn't contain A1. If it contains A1, every value is 2, and then you are happy, right? And like, okay, fine. And if it is, then this is just a cardinality constraint. So, I mean, of course, suppose it doesn't contain, look at the case, I mean, if it doesn't contain, A1, if it, yeah, I mean, so look at this, okay? So it is, suppose this is 2 minus 1 is 1, okay? And no, f of s union E is going to be 2 minus f of s, which is going to be 1, so 1. And this is the same change, no? Cardinality minus cardinality cannot be, like, if it's just basically how much we added, how many extra elements I added here. That's it. That's it. So this is submodular. Okay. But now notice what my greedy algorithm will do. It will add A1 to my solution first, right? Because every other element gives me utility 1, this gives me. But can I add anything more after this? No. Because after the, once I add this, my utility is not going to increase. Right? So this algorithm is going to return me an x, so that f of x is equal to 2. But what is an optimum? I could have just avoided 2 and taken any elements from here, k elements from here, I would have got k. But this k is unbounded, or if I would have been working in, say, unconstrained condition, then it is like n minus 1. So it is like 2 divided by n minus 1. So this is like some factor n approximation. Okay? So this grid is not going to work. Maybe the function which I wrote before doesn't work for all that I know. Okay? So this is very clear that this grid is not going to work. But is it because, okay, is it because that we went from first to the last element? But what happens if I just reversed it, the process? What I mean by reverse this process? Look, I was trying to build a function. Okay, I was trying to build my set A. But rather than building, I said, let's take n and let's delete an element. That's like a reverse greedy. Okay, so let's do this, what I call reverse greedy. So what is A0 is equal to n. So let's start with universe. So I will not say union, okay? I will say minus. If I subtract this, then just subtract. Look, for each item, what is this? So ai will be ai minus I1. So basically I'm saying let ui in n, which maximizes f of ai minus ui minus f of a minus 1, right? Then I set, if this, and I set this up, right? So this is like a reverse greedy. I started with a whole set, hoping that, look, we made mistake last time because, I chose an element in the beginning itself. So let me start and let's try to delete elements one by one, right? And see if we are very happy. What happens to this greedy algorithm?
For this example, does it delete those elements?
In fact, what I could have done, no need of I equal to k, like even if I do not work, say, unconstrained submodular function for now, right? So I will just say, while there exists ui in n such that f of ai minus 1 minus ui is greater than f of a minus 1, what should I do? I should make ai equal to ai minus 1 minus u. I just do this. Well, there is some element which, so basically what I'm trying to do, I started with n, and if there exists an element whose deletion gives me, rather than increasing the maximum value, let's just do this simple greedy. Because last time we were actually not, I mean, even if actually you can prove that,
Won't work for constrained version, right?
huh?
This will not work for constrained.
It will not work for constrained version, fair enough. But you can make it work it also for the, okay? Because all you need for your greedy algorithm, you don't need maximum, minimum, nothing. If there exists, like for the monotone function, I have some set. If there exists an element which increases my marginal, you can just add it. And this is what we did last time and analyzed it. You don't have to do max or something.
But here it may stop in the stage where A equal to say k plus 10.
Yeah, it could.
Then you
This is why it's unconstrained. Unconstrained. Okay? All I'm saying that, like, even for the unconstrained version, if I did for monotone, this will be perfectly fine. Now let's see what happens. What is that called? Let's see what happens if so if you notice, look at if you have a function f, okay, which is from 2 to the power n to r positive, then define f tilde, which is from 2 to the power n to r positive, and for every a, you map it to n minus a. You can show this is also submodular. Okay? Now what happens if we try to do this? Right?
starting with 0.
Yes. Okay. So notice that because of the condition, okay, if opt maximizes f, if opt maximizes f, then f of n minus opt maximizes f bar.
Okay, it's not cardinality. F of n minus a.
What? No, it's just n is universe.
Okay. It is a maps to.
To f of n minus a.
Oh, it's f bar. Okay.
So the definition of f bar is a maps to f of n minus a. Right? Here a was mapping to f of a, whatever that function. Okay? So now what happens? Okay? I want to claim that if f opt maximizes f, then f of n minus opt maximizes f bar. You can prove using contradiction. Okay? This is not very hard to see. Right? Now, running the reverse greedy algorithm on f bar is same as running normal greedy algorithm on f. So this example will still hold. Okay? Even if you did not understand, all I wanted to say that if this reverse greedy doesn't work, but what we will see for all the algorithms, a combination works. Okay? Okay? So reverse greedy does not work. That's all that I wanted to claim. Okay? And reverse greedy with respect to f bar is same as, with respect f bar is same as normal greedy with respect to f, right? Because what will you do? Here it will be empty set. Because what is, if I'm running this with f, right, reverse greedy, so what will be, right? I will start with universe, right? But what is what will be the function of this? Right? It will be empty set. So things will hold. Okay. So this is not something which I wanted to spend more time on. So let me, okay. So all we know for now is that while do we have a very good theorem for monotone function, we do not have very good function, very good algorithm for arbitrary function. And our idea is for the today is to design 3-4 such algorithms today. Okay? Okay. Okay. So what we are going to do first, we are going to do first unconstrained submodular maximization. Unconstrained submodular maximization. Okay. And then we'll get to the constraints of submodular maximization because it exhibits some of the very nice properties of submodular functions, as well as you will see a lot of probability calculations, which is good. Okay. So now what happens is the following. Okay. Now if I asked you an algorithm for max cut, what algorithm will you do me? Which will have very good approximation. Randomly pick a subset with probability half. If you pick a set A of P, I randomly pick some subset, right? With probability half, I pick an element here in this set. Then we can show that it has at least this algorithm will return a max cut with probability half, like not probability half, with ratio half. Do you agree? Because at least half the elements will be going outside. Max cut can only be M. So this is. Now what happens if we do similar idea for this? Okay. So here's my algorithm. Algorithm is very, very simple. What does it does? Okay. So here's my algorithm. Algorithm is done. So let N of P denote the set, in fact random set, okay, denote the random set of N where each element, okay, is sampled uniformly with probability half. So this is what I do. Right? So what do I go through each element and I make a set N of P. How? I go through each element and with probability half I keep it, with probability half I don't keep it. That's it. This is your algorithm. Is the algorithm clear? This is exactly like max cut. I have a graph or max die cut, right? Direct. That will give you 1/4 approximation actually because you can only say M by 4 elements are going one side. So this is my end of my algorithm. Okay. All we have to do is to analyze this algorithm, and this is a funky thing to do. Okay. So this is a very good algorithm actually. Okay. So you randomly pick a subset of your universe with probability half. And that tells, if this algorithm we understand, then that tells us how we go about improving it, not improving it. But the algorithm is very simple. I have picked, it's exactly like max cut. With probability half, I picked up an element. Okay. Okay. Okay, so this is a lemma which is used crucially everywhere in all this, or the spirit of this lemma. Okay, so let's try to prove what happens to this. Okay, and so what is my lemma? My lemma is very simple. Okay, let f be 2 to the power n to r be submodular. Okay, and this is non-negative. Okay, maybe I should write it. Let's see if we need it. If we need non-negativity, if we don't need it, then we don't need it. Okay? So if we need non-negativity, we'll add it to this. Denote by n of p, okay, a random subset. Let's not let's a of p, a random subset of a. Okay, so I fixed a, which is a universe of n, and I just pick ap, a random subset of a, where each element in a, okay, appears with probability p. Okay, then what I'm going to show to you that expectation of, let me call this function g. Okay, so that this lemma is like, it has nothing to do with this f. We can invoke this lemma with putting g equal to f, putting a equal to n, so that we can invoke all this. Okay, so what does it tells us? Expectation of g of a of p is at least 1 minus p times g of phi plus p times g of a. What does it tells us? That if I have a sum, right, then the expected value of this is 1 minus p times expected value of the empty set. So if it had been a non-negative function, then this will be some non-negative quantity plus p times g of a. Okay. Suppose we prove this lemma. Okay. Okay. Suppose we prove this lemma. Let's try to suppose, and we'll come back and prove this lemma. Let's see why does this imply that this is a good factor approximation. Okay. So we need another lemma. Maybe I should give you first proof for this. Okay, let us prove this. Okay. Yes. No, it's a random subset of a, some a.
But A itself is, I think,
A is some subset of n. AP be a random subset of A, which is a subset of n. So I'm doing only sampling from A, not from the n. From here only I have done sampling, right? So that like I'm making as more liberal algorithm as possible. Okay. Now let's try to prove this. So we are going to prove this on induction on the side of A. Right? Proof is by induction on the size of A. Okay. So if mod A, if A equal to empty set or A equal to phi, right? If A equal to phi, then there is nothing to prove. This is like this trivially holds because you are not going to pick up anything. Right? You're not going to pick up anything, so this trivially holds. Okay? So now I'm going to assume, so the base case holds. Right? So now what I'm going to do is, let us assume that we have A prime, A equal to some A prime union some new element x. Okay? And x is not in A. Look, we are not applying induction on this. We are applying induction on A, which is subset of n, right? So I told you, right? Here is A. So I'm going to prove this for every A. So how do I prove? I'm going to prove this with the cardinality of A as my induction. A is equal to A prime x, okay? Then notice something. Then A of P intersection A prime, A of P intersection A prime is contained inside where? A prime of P union x. No, it's not even required this. If I look at A of P, I take with its intersection, then this is contained inside A of A prime of A. So A of P intersection A prime is contained inside A prime. Right? This is a very vacuous system. And what is this? Where each elements in A prime, where each element in A prime appears with probability P. Let us denote this by A prime of P. Right? So from A prime we are sampling a subset with probability P, and because this is what we have fixed, so this is what we are going to use. This is just simple stuff. Okay. Look, I am also going into very uncharted territory or whatever it is called. Okay. Let S equal to A of P, okay, and T equal to A prime, and let's use some modularity. And use some modularity. What will this imply? This will imply, right, if I do normal thing, G of A of P plus G of A prime is greater than or equal to G of A of P intersection A prime plus G of A of P union A prime. Right? Now, what is G of AP intersection A prime? Is A prime P. So this is G of A prime P. And agreed? What? What is AP intersection A prime? It's contained inside A prime where each element in A prime appears with probability P. And let us denote this set by A prime P. I've done it. Okay? So now what is G of AP? This implies G of AP is at least greater than or equal to, let's pull this here, I'll tell you why, AP union A prime plus G of AP A prime P minus G of A prime. Right? Here I can apply induction because A prime is a because this is with respect to A prime, where A prime has a strictly smaller set than A. So I could apply induction here to get inequality of this form. Okay? Okay. So now let's try first, but we'll do that first later. Notice this is a random variable. A of P is a random variable. A of P union A prime is a random variable. A prime P is a random variable, but this is not a random variable. Right? So random variable, random variable, random variable, and what is the function this random variable? It's just a G function. Right? So basically here, this is a random variable, this is a random variable, this is a random variable, and this is not a random variable. This is just a function. Okay? And but now what is a random variable? So G, what is a value? If x is a random variable, then you have to give a value from 2 power something to the power some r. So you just take this and just map it to G of A. That's it. Okay. So now I take expectation both sides. Okay. So what do I get? Because this statement is like expectation. So what will I get? Expectation of G of A of P is at least expectation of G of A of P union A prime, right? Plus G of A prime P minus G of A prime. This is what we get, right? Now by linearity of expectation, what can I write? I can pull this out here. G A prime P plus expectation of G of AP union A prime minus G of A prime. Right? Here let's apply induction. So by induction hypothesis, this is less than equal to what? It is less than equal to so we'll apply induction here, okay? Okay. Okay, so we'll apply induction. But let's look at this thing. This is more important for us because here we'll apply induction and something will happen. Now let's look at G of AP union A prime, okay? Union A prime. So what happens? With probability P, right? With probability P, I will add this element X to A of P, right? So what is this? Either this is going to be, what is this set going to be? This set is going to be either A prime P union X, or is it going to be just A prime P? This set is going to be only these two.
It could be A prime or A.
No.
Because A prime is larger.
Right. What am I writing? Okay.
Either it is A prime or A.
Sorry, either it is A prime or it is A prime union X. Okay. Now, when is this going to be A prime union X? When you are going to include X in A of P. But that happens with probability P. And this happens with probability 1 minus P. Right? Okay. Okay. So now, if I wanted to write this guy's expectation, what will I write? If this guy's expectation, okay, so let's write it down and we'll, so this is just a small like side computation. Now let's apply induction here. So what will this give us? At least 1 minus P times Z of empty set plus P times G of A prime, right? Plus, now let's apply this. So I will write, what is the expectation of G A prime? It's G A prime, right? So we'll get minus G A prime sitting here, okay? But now if I apply, as all of you told me, if I apply here, what I'm going to get? I'm going to get P into G of A prime union X bracket
Close even with the G of A.
or plus 1 minus P of A prime. I think this is what we are going to get, okay?
Don't close that.
Because I have to multiply, oh right. This is this times this, okay? Okay, so let's see if anything is making sense to me. But, okay, is A, right? So this I can write it down, 1 minus P times G of empty set plus P of G times A prime, okay, plus P of G times A, right? Right? And here if I get it, what will I get? Plus G of A prime minus P of G of A prime minus G of A prime. So this and this will cancel out. This and this will cancel out. So what will be left with? 1 minus P into G of empty set plus P times G of A. Done. Okay? So this is fine. Okay? And every paper on, most papers rather, on submodular function optimization, where it's an arbitrary function, you get some one form or this of this lemma, like some version of this. Okay? I will do another analysis for this in a minute. So I need another lemma. Okay? So this lemma tells us something interesting. Okay? But another lemma. Let Fp to the power n to r. But did we use non-negativity here anywhere? Even in the base case? I don't think we used, at least induction hypothesis we have not used it. No? For algorithm analysis we need, that I know why and how.
The first two, three places that are greater than or equal to
Yeah. That is not because of some, this is just because of submodulatory, right?
and then
This is equality because of the way our sets are defined.
yes, the third one.
This is just a copying of this, right? This is just a copying of this, like moving this. Then I took expectation. Then I apply linearity of expectation and induction hypothesis, right? So at least here I didn't use anything, okay? But what about the base case when A is empty set? Huh? So what is expectation of G of phi? Is G of phi, right? Because what is A of P? You're not going to pick up anything because there's no element. So it is expectation of G of phi is G of phi. So let's see what happens here. G of phi should be greater than or equal to 1 minus P times G of phi times P times G of phi, right? So what does this implies? G of phi, nothing, because minus PG phi will get cancelled. So all it says that G phi should be greater than or equal to G phi, which it is anyway. So we did never use non-negativity. So at least for this lemma, I don't need non-negativity. Okay, this is just a point. For this lemma also probably we don't need. Be submodular. This is enough. Okay. Let A comma B be subset of n. A and B may not be disjoint. Okay, A and B may not be disjoint. A, B subset of n. B two sets. and let A of P, B of Q, okay, they're independently sampled subset with probability P and Q respectively. Okay. So with two different probabilities, I'm going to set like A and B. A of P, where each element is picked up with probability P. In B of Q, where each element is picked up with probability Q. Okay. Then, what are we proving? Expectation of f of AP union B of Q, okay, okay, is at least 1 minus P, 1 minus Q, f of phi plus P times 1 minus Q, P times 1 minus Q, f of A, right, plus 1 minus Q, Q times f of B, plus PQ times f of A union B. Okay? Okay. Now let's see if I prove this lemma, why are we done? Okay? Because I needed to do this to get to this. Okay? It's a long proof. So, but let's prove the theorem. Okay? So let's get an approximation algorithm for this using this lemma. Okay? So how I'm going to apply this lemma is just something very simple. Denote the optimal set by S. Okay? And its complementary set n minus S by S bar. Okay? Then I claim to you, so whatever the random sample you picked up, n of P or n or whatever you want to call it, okay? N of P is nothing but we should basically say n of half. Okay, uniformly with probability half. So n of half is f of half union f bar of half. Do you agree? Look, every element either appears here or appears here. Right? So I sample first from here, sample something from here. Right? So this is what n half is. Now, what is an expectation of, let's call this n half, this is what I have picked up, is at least, now look at here, P is half, Q is half, this is 1/4. Right? Okay, what is f of phi? Right? Something is f of phi. Right? Because f of phi is there. What is P into 1 minus Q? Is again 1/4. And what is f of A? A role has been taken by S. So f of S, which is opt. Plus, what is this? Let's go here. 1 minus Q, this is another 1/4, f of S bar. Okay? And what is this? 1/4 f of n, because S union S bar is n. Okay. Now notice, now because of non-negativity, this is greater than equal to 0. This is greater than equal to 0. This is greater than equal to 0, right? So it implies 1/4 times f of s. Here we used non-negativity of f. So this gives us factor 1/4 approximation for this. Now suppose I had symmetric function, symmetric submodular function. Suppose we had symmetric submodular function. Arbitrary. What does it mean? F of x is equal to f of n minus x. Right? So if f of s is opt, f of s bar is also opt. So for this you will get expected n half is at least half times f of s, and then you are done, right? So for symmetric submodular function, symmetric non-negative submodular function, we will get factor half approximation, otherwise we will get factor 1/4 approximation. Okay. So everything depends on this lemma, and once we have this lemma, we can apply this lemma, and the proof of that lemma will apply this lemma a couple of times.
So it generalizes both max cut and direct cut.
Yes, it generalizes everything you can think of. Right? Okay. We'll get there. Okay. I'll tell you a trick here, which is I'm going to tell you now, and after that I will never going to use, like I will just say that we'll use it, like we can apply exactly the same idea. So let's call it lemma 1. Let's call it lemma 2. Okay. So now I'm going to write proof of lemma 2. Okay. So what is the proof of lemma 2? Okay. Consider A of n of p equal to r. I'm going to call this r. Okay. And define g, a new function. Here it is f, so I'm going to use some new function g of t as f of r union t. So I fix some npr and this. So, okay, so basically what I'm doing here, I'm conditioning on np, I'm conditioning on, suppose, condition on the fact that n of p equal to r, let's define this function. Okay, claim g is submodular. Do you want a proof, or are you good with the proof? Okay. So what is this? G of x plus g of y. I have to show that this is greater than or equal to g of x union y plus g of x intersection y. Agreed? This is what I have to show. Okay. Okay. So what is g of x? G of x is going to be x union r, because, sorry, it is going to be f of x union r plus f of y union r, right? I have to show this is at least equal to f of x union y union r. Because x union y, right? So x union r union y union r is nothing but same as x union u union r. Plus f of x union r intersection y union r. Y intersection r. No, union. Right? So this is equal to f of x union u union r, okay, and this is what f of r union, because r is common in both, union x intersection y, right? But what is this function? This function is nothing but g of x, this function is g of y, this function is g of x union y, right? This function is g of x intersection y, right? And then we are done. So this is submodular. Okay. Okay. Now, what is an expected value of g of b of q? I apply this lemma. Right? I have to compute f of AP union BQ. Okay? I have conditioned on some n of p equal to r for now. So I'm just what is expected value of g of b of q? I can apply this lemma. Right? It is nothing to do with.
Okay, in lemma 2, n of p is not defined. It is that.
What?
You are proving lemma 2, right?
Yes.
So n of p is not defined. Is it a of p?
Sorry, it should be a of p. Why am I writing this? Yeah, a of p. Okay. Okay. So we have condition on the fact that a of p equal to r. Right? So now I'm going to apply lemma 1 on this. So by lemma 1, what can I write? This is greater than or equal to 1 minus p times g of phi plus p times g of b. Right? Okay. But this is equal to 1 minus q times g of r, because R union empty set. Completely correct. Okay. Now I want to uncondition this. Okay. And this is something which, even if I do unconditioning, I will get exactly the same sentence. Okay. So let me tell you what I mean by this. Okay. Let us do. Look, I was doing this calculation condition on the fact that AP equal to R. So like I should have written here slash AP equal to R, which I did not write. Right? So basically what I meant by conditioning is like this is not an expectation. This is an expectation given G of AP, right? When R equal to, this is what it is. Right? So this is what I was computing, please. Okay? So now I want to uncondition this. Okay? Do unconditioning. And this is a trick which you apply 1,000 times. So please don't ask me after this again. Okay? So what is your what is G of BQ? Is this. But What is the value of this? Do you know what is the meaning of this? This means you sum over whatever the value this random variable takes times, right? Times like probability of this and this. This is what by definition is. What is an expectation of x given y equal to y is equal to summation, okay, x in the range of x, probability of x equal to x. No. What am I writing? X probability x equal to x, y equal to y. This is what it is. This is the value of this. Okay. Sorry. So I go over this and I can do this. Okay. So in fact, so now let's try to understand what is happening. What am I interested in? I'm interested in computing okay expectation of what is this G of BQ? It is nothing but f of BQ union R given that R equal to AP. So this is what I'm interested in. So now I'm saying that look, now I'm unconditioning this. So f of BQ union AP, okay, is same as summation x in A omega, okay, probability that A of P R equal to x, right, probability that R equal to x, now into expectation of f of A of P union B of Q given that R is equal to x. This is what it is. Huh? Oh, A omega is all subsets of omega, all subsets of A. I shouldn't say A omega, I should say omega A. All subsets of A, right? Because I don't know which random subset I'm going to get it. So what is this? Like, what is an expected value of this? Expected value of this is now look, either this AP can take this or this or this or this. So what is the probability that it takes this times condition on the fact like, okay, given that this is an expectation, right? So this is how you do unconditioning, okay? Now what is this equal to? This we know what is this equal to.
R equal to A of P, right?
R equal to?
A of P in this expression.
Yeah, R equal to, so I shouldn't say R equal to F of A of P, I should just say X, R equal to X, because then it's like a variable. Look, I'm interested, this is a random variable. A of P is a random variable, right? It takes different set of values. What does it takes? It takes an X in omega A, right? So, but whenever it takes this, so this is what I'm interested in computing, given that probabilities are equal to X. But this probability we know how to compute. Huh? What? What? You're right. Okay. Do you agree to this? Okay. So this is same as summation, say summation, or at least this probability value I know. It is nothing but p times cardinality of x, right? And now this I have already computed that quantity here. What is this R union BQ? Is nothing but expectation of G times BQ given R equal to X. I have computed that value for you, right? I have computed that value for you. So this is at least, because now I'm going to apply that inequality, summation x in omega A, p times mod x. What is this value? It is going to be equal to 1 minus q times, what is this? F of x, because now R is x or whatever you want to call it. What?
The probability P R equal to X.
Yes.
P raised to X and 1 minus P raised to minus.
Oh, right. 1 minus p times a minus x, right. Yeah. So whatever that, let's call this probability p of x. Okay. Getting an x, this is a probability. Okay. Maybe I have confused with some inequalities, but this is fine. Because I don't think we should.
You need exactly equal to that, not superset.
What?
You need exactly equal, so you need that 1 minus P to that.
1 minus p2?
Okay, you were saying.
No, that's okay. That's okay. That we don't need it anything. Okay. But what is this? This is what I'm replacing here. 1 minus q times f of x plus q times f of b union x. This is what it is. Agreed? Okay. Now let's try to compute this other way around. Okay. Okay. So when I uncondition it, this is all that gets. Now let's compute this other way around. What is an expectation of 1 minus q times f of a of p plus q of f of a of p union b. Notice here only a of p is a random variable in this, p is fixed, right? So what is an expectation of this? I don't know what a of p takes, so I just go on value substituting that, which is same as summation x in omega a, p of x, whatever the probability we computed here, okay, times
X is a subset.
wait, right, and 1 minus q times f of x, right, plus q times f of x union b. Agreed? This expectation is exactly this. Probability times the value it takes. Right? And this is the value it takes, this random variable. Because look, I could have just taken 1 minus q out, I would have taken q out and then done it. Doesn't matter because they are constants. By linearity of expectation, this is exactly what we are going to get. okay, but what did we get? This term and this term are same. So what can we say then? Then I can say, right, expectation right. So I have computed expectation in two ways, okay. So what does it imply? So this just implies that this expectation f of bq, f of ap union bq is greater than equal to uh, right hand side top, right, 1 minus q times f of a of p, okay, plus q times f of ap union b. Agreed? Like this is what we have been able to show from here. Right? Now let's try to apply linearity of expectation. If I apply linearity of expectation, what will I get? 1 minus q times expectation of f of a of p, right, plus q times expectation of f of a of p union b. This we know how to compute it. This is exactly what we have computed here, right? Okay. This is what we have computed. No. What we have computed is this quantity. Yeah, lemma 1. This is the quantity we have computed, right? Expected value of this is this. We have already computed, right? So this I can write at least 1 minus q times, what is f of ap? 1 minus p f of empty set plus p times g of a, g of f of a. Sorry. Plus q times expectation of f of ap union b. Okay, let's try to understand this term. Okay, let's try to understand this term. Okay, let's try to understand this term. Okay, let's try to understand this term.
P and B of Q are same, right? In those expressions.
What?
P and B of Q are same in this expression, right?
In which expression?
What was your
Yeah.
P and B of Q, they are same, right?
No.
They are different.
They are very different. This is B is a whole set from you are going to sample this.
Oh, okay. I see. Okay.
So now I'm going to define a new function h, okay, from 2 to the power a to r positive or whatever. H of s is going to be h of s union b. Okay, you can show this is also, and you can show this is submodular function. Okay, so what does it mean implies? Expectation of h of a of p, I can use this, right? So expectation of h of p is at least greater than equal to, what is this? 1 minus p times, no, it's not equal. What is this? This is going to be h of phi, because we are applying with respect to h, plus p times h of a. Now, this is, what is this? 1 minus p, this should not be h of this. This should be f of s union b. Otherwise, what is the meaning of the difference, right? So, this is equal to f of b plus p times f of union b. Let's substitute this here. Ah, God. Okay. 1 minus q, 1 minus p, f of phi plus p times f of a, close the bracket, plus q times, please can someone tell me from here, it is 1 minus p f of b union b. Now, if I open this up whole, right? So, 1 minus p into 1 minus q into f of phi, that's the first term, agreed? 1 minus q into p f of a is a second term, right? Q into 1 minus p f of b is the third term, and p into q f of a union b is the last term. So, we are done. Okay. So, what did we learn? God. Okay. Okay. So, whenever I will say unconditioning, this is exactly what I will mean. And I will, from now onwards, I will just write down this term, right? Like in various ways you can do. So whatever, so what, like here it was double conditioning, but if you do just some simple conditioning, then it will come exactly the same kind of things. I'll show you one example of this, okay? So let's talk after lunch.